Hey everyone, welcome to This Explainer. Today we're diving into some absolute magic. Specifically, how engineers are mathematically squeezing massive AI models onto edge devices, all without literally melting your smartphone's hardware. If you've ever wondered how these absolute behemoth language models could ever fit inside the phone in your pocket, well, you are definitely in the right place. Let's get into it. Here's a quick roadmap of what we're covering today. First, the on-device AI problem. Then we'll look at the precision bottleneck, introduce model quantization, walk through the three main workflows, explore some advanced techniques, and finally take a peek at the future of edge AI. All right, starting with Section 1, the on-device AI problem, why massive models don't fit in your pocket. Okay, so to understand why running a large language model on your phone is such a massive hurdle, we have to look at the sheer physics of memory. Modern generative models have hundreds of billions, sometimes a trillion parameters. That requires a staggering 400 gigabytes to over 4 terabytes of RAM just to hold the model's rates. Because each parameter is typically a 32-bit float taking up 4 bytes of space, the memory footprint just blows up incredibly fast. It's completely prohibitive for any edge device with strict memory limits. Moving on to Section 2, the precision bottleneck. It's all about how computers do math. You see, how computers represent numbers dictates absolutely everything about an AI model's size. Think of single precision, or float 32, as packing your entire wardrobe for a 2-day trip. It takes 32 bits per number. Sure, it gives you this massive dynamic range, but the memory footprint is just huge. Now contrast that with half precision, float 16, or integer int 8. It's like bringing just a toothbrush and a change of clothes. You bring the bare essentials, the suitcase finally snaps shut, and you get a beautifully tiny memory footprint. Look at this breakdown of standard AI formats. Up top, we have float 32. 32 bits, massive range, the absolute default for training. But check out the real game changer here, BLE float 16, or brain floating point. It intelligently halves the memory usage down to 16 bits. But, and this is key, it keeps the exact same 8-bit exponent width as float 32. So it retains that ridiculously vast dynamic range of 10 to the negative 38 all the way to 10 to 38. It's super robust for training large models, but completely skips the memory bloat. Which brings us to Section 3, enter model quantization, the AI shrink ray. So, the million-dollar question, how do we actually shrink these massive math matrices to run on our devices? Well, that's where quantization comes in. By definition, it's the process of reducing the numerical precision of both a model's weights and its activations, the intermediate data flowing through. By shifting from float 32 down to int 8, it literally acts like our shrink ray. It linearly maps those giant floating point numbers into small, neat integer boxes using specific scales and 0 points. It's wild because the model can still approximate real values using highly efficient integer math. And the savings? They are immediate and they are massive. Moving from a 32-bit float down to an 8-bit integer instantly chunks out 75% of your model's memory footprint. Just like that, 3/4 of your storage requirement is gone. Plus, if you're running on supported hardware, you can literally double or quadruple your inference speed. It's a total win-win. Now for Section 4, the 3 main workflows. Let's look at how to actually apply this shrink ray in PyTorch. Okay, so with the math and the stakes laid out, let's talk engineering. If you're a developer using a framework like PyTorch, this naturally raises a huge practical question. At what point in the AI's lifecycle do you actually shrink the weights? And what about the activations, the actual data moving through the network? Well, the first and honestly the simplest approach is dynamic quantization. In this workflow, the model's weights are permanently shrunk down into int 8 ahead of time. But, and here's the catch, the activations stay in full float 32 right up until runtime. Then they just get quantized on the fly. This is absolutely fantastic if your model is memory-bound, like standard transformers, because you don't need any calibration data beforehand, and it still drastically cuts down the size of the weights. Then we have post-training quantization, or PTQ. This one statically shrinks everything ahead of time. It's kind of like a recipe. First, you fuse operators together, like convolution and ReLU, just to save on memory access. Next, you insert these clever little things called calibration observers and feed the model some representative data. The observers watch the data and learn the activation ranges. Finally, you convert the whole shebang to full int 8 execution. Boom, you've shrunk the network without needing to retrain a single thing. But what if you have a highly sensitive model, like a vision model where accuracy drops if you even look at it wrong? For those, we use Quantization-Aware Training, or QAT. This method simulates precision loss using what's called fake quantization right in the middle of the training process itself. So the model is actually learning and adapting to the in-state math noise while it updates its full precision weights. As you might guess, this yields the absolute highest accuracy out of all three methods. All right, Section 5, Advanced Quantization Techniques, pushing the limits of compression. So as we shift into the era of hundreds of billions of parameters, those standard uniform methods we just talked about, they probably start breaking down and ruining accuracy. That's why we have this modern quantization arsenal. We've got GPTQ, which uses second-order error compensation to literally fit a 175 billion parameter model on a single GPU. We have SmoothQuant, mathematically scaling activations for training-free 8-bit quantization. Then there's AWQ, protecting the most salient or important weight channels from losing precision. And rounding it out, we have EXL2, mixing bit allocations dynamically, and palletization, which clusters weights using k-means. Just keep in mind, guys, this whole process is a constant tug of war. These advanced tools are meticulously designed to balance size, speed, and accuracy. They do this by tackling either compute-bound bottlenecks, where the chip just needs to do the math faster, or memory-bound bottlenecks, where we desperately need to take the pressure off external memory bandwidth. And all the while, they have to keep the model's brain totally intact. Finally, let's jump into Section 6, the future of Edge AI, the final boss of quantization. Now we're out on the bleeding edge, and things are getting incredibly complicated. As AI evolves to handle text and images at the exact same time, we've run into a massive hurdle. Can we actually compress these vision language models without breaking their delicate cross-modal understanding? I mean, how do you shrink a model that is both looking at a picture and talking to you about it at the same time? Seriously, vision language models are the final boss of quantization. The big issue here is that vision and text activations have completely different statistical distributions. And more importantly, they're cross-attention fusion layers, which act as the delicate mathematical bridges connecting a patch of an image to a text token, are insanely fragile. If you compress their mathematical precision even a bit too far, the model literally forgets how to connect what it's seeing with what it's saying. So what's the workaround? Right now, engineers are using a really surgical approach called hybrid quantization. You take aggressive int8 or int4 quantization and apply it to the robust text layers. But crucially, you protect those fragile cross-modal fusion layers by keeping them in high-precision FP16. And while you're doing that, you leverage progressive quantization-aware training on the vision encoders, so they slowly adapt to lower precision over time. As the source material puts it perfectly, as vision language models become more prevalent in edge AI, a new generation of quantization-aware toolchains will be essential to unlock their full potential. The reality is, right now, there isn't one magic click-a-button framework that compresses an entire multimodal pipeline perfectly. The future entirely depends on us building these smarter, more adaptable toolchains. So as these mathematical shrink rays keep getting better and better, moving from basic static quantization all the way to packing supercomputers right onto our mobile chips, I want to leave you with one final thought to chew on. What are you going to build when a trillion-parameter AI fits perfectly in your pocket? Thank you so much for joining me on this explainer, and keep exploring the incredible math that is shrinking our world. See you next time!